Good evening, everyone. Just wait for a few more people to turn up. I'm not quite sure if they will turn up, actually. Hopefully, we have some decent numbers. Victoria, good to see you. Firstly, let's see how you feel at the end of this. But no problem. You're very welcome. Oh, look at this. Is it mostly my class here? If you are from another... Well, if you are an AS student at Oldham Sixth Form College, then do please say hello in the chat. And it would be nice to know. Obviously, I know my students. But any other students from any other classes, feel free to say hello in the chat and let us know which teacher you have day to day. That is right, George. Yes. I'm not sure why you're sunburnt, Victoria. You should be inside revising. Unless you went outside and revised. Hello, hello, hello. I don't know who any of these people are. I am Max. Fancy you being here. I'm sure you did your A-level exam on Wednesday. You must have come back for some AS revision for some reason. Hello, Phil and Matthew. Oh, Phil and Matthew. Yeah. Dream team. Hi, Shirley. I don't know if you're saying like hi, Shirley's in I'm Shirley. I'm not, I'm John. But I get your point. Now what we're going to do today is we're going to go through some AS revision topics from the topic list. And we're going to recap some stuff. It's completely up to you what we can do. If you want to do some exam questions, if you want to do some solid revision, I'm happy to do anything. What I will do is I'll show you the topics from the revision list and we'll hit those because we can kind of forget about everything else. So let's jump straight in. You know, this is all being recorded, by the way. This will go directly onto YouTube after. And what I will do is I will timestamp each topic as I go through it. My last 3 live streams have been 3 hours long. So we can do it. We can go 2 hours, 1 hour, 1 hour, 1 hour and a half. It's absolutely no problem. We'll see how far we get. Okay. So those things in red, if you did jump onto the A2 live stream just to see what was going on there, you might have seen a very similar setup. You have more components to cover than the A2 students. Well, not topics, not components, more topics. So you have 17 topics that you should have covered this year. You've not covered them all because obviously pandemic. But be rest assured that you will cover all of them topics in your second year also. So plenty of time to cover all the topics. Those ones in red are the main areas that we're going to hit from the topic sheet. We have hardware and communication, logical operations, data transmission, data representation, data types, data structures, and also algorithms and programming. So number 9, topic 9, that comes under your programming teacher. Topic 5 comes under your programming teacher. And topic 4, 1, 2, and 3, said in a random order, don't ask me why, that is covered by your theory teacher. You all have a theory teacher and you all have a programming teacher. It just so happens that I do both, so I'm in a perfect position to actually go through this. So what I'll do is I'll start off on recapping the von Neumann architecture. If you want a specific topic covering or a specific thing, then put it in the chat. I will try and get to it. I can see the chat. I have 3 screens here. I can see the chat. I can see what I'm presenting as well, which is also a bonus. But let's get cracking, eh? Von Neumann architecture. How many people have we got before we start? I don't even know. 19. 34 playbacks. Okay. Will you go through everything? That is such a Victoria question, isn't it? Honestly. Will you go through everything? Unbelievable. How many flashcards have you got now, Victoria? What number are you up to? By the way, there is a delay as well. There's a 6-second delay on this. Is Louis here? Where's Louis? Okay. Yeah, can't keep track. Now then, components of a processor. You're going to have to be able to, in the exam, potentially recall all the different components of the processor, explain their use, and explain how you get data from a secondary storage device all the way to the CPU and the steps it takes to get through those. So that will include the fetch, decode, execute cycle as well. But the key components that make up a processor are the arithmetic logic unit, the control unit, and the registers. Now the registers, they boil down into a few more things that you might have to recall, like the program counter, memory address register, that sort of stuff, a memory data register, and even the accumulator, the ACC, which actually isn't inside the register part of this diagram. There we are. It's inside the ALU, the ACC, because it's a special register. Now that diagram, you also have to be able to look at the diagram and interrogate it. So you might get this diagram here. Let me just get a pen. You might get this diagram and you might get these shapes. So you might be asked to draw these shapes, but these might be omitted from the diagram. So you'll be asked to actually say, what is this shape here? And you might have to say, well, this is the ALU. What is it responsible for? It is responsible for the arithmetic logical calculations inside the computer. So any numerical, what am I on about? Arithmetic operations that carried out are done by the ALU. And you'll have to talk about each one. But what you're looking at on screen is the von Neumann architecture. It's not changed for an awful long time. And this memory here, you might be wondering what this memory is. That is random access memory or cache memory. Information comes in through an input device. The data bus takes the information and passes it and stores it in a register. The control unit is in charge of all the instruction decoding. And the CPU itself contains the ALU, registers, and the control unit. So remember that shape, it's like a V. There's a rectangle, an oval, and you have 3 buses as well. You have the control bus, the data bus, and the address bus. You don't have to get specific about what they do. If you're asked about buses, all you have to do is say that a bus's role in the von Neumann architecture is to transfer data from one place to another. If I'm losing you at any point or you don't understand something I said, feel free to put it in the chat and I'll answer your questions. What are input devices? That can be anything from keyboards to mice to the visual display unit, so a touchscreen. Output device, again, visual display unit, screen, speaker, printer, that sort of thing. Now, arithmetic logic unit, responsible for all calculation and logical operations. Now, what do we mean by calculations? We're talking floating point multiplication, integer division of numbers. We're talking while logic operations, so looping, iteration, that kind of thing, and comparison tests. So comparison tests are things like greater than, less than, greater than or equal to, less than or equal to, or even not equal to. So logic. Remember, and, or, and nots, that's also logic as well. So the ALU also acts as a conduit for the input and output to and from the processor. So what that means, the conduit is a bridge basically between inputs and outputs. Hello, Mahadi. Hello, Mummy. Now, what you're looking at there, do you need to know what calculations they do specifically? No. But if you're asked to give an example of the kind of thing that the arithmetic logic unit does, you need to be able to recall one of those bullet points there. So if you do electronics, you might be able to recognize some of those shapes in that diagram. That basically, they're just logic gates, really. And that's what the arithmetic logic unit is all about. Now the control unit, or the CU, is also another key part of the processor. Now it manages the execution of the machine code and it sends something called control signals to the rest of the computer. So once it's decoded the information, it will work out exactly what needs to be done, and then it will send out its control signals to tell other parts of the computer to kick in, do whatever it needs to do, or output or input something. Now obviously, control signals from the control unit are sent via the control bus. So control unit produces control signals sent via the control bus. Now part of the control unit's job is to synchronize instructions and do them and produce them in the correct order. Yes, it does, Firas. It does. Now, when we synchronize instructions, you might have heard of this before. You have a clock cycle, which is inside the CPU, and the clock ticks very, very quickly. The faster your internal clock pulses, because remember, a clock cycle is the time taken between two pulses of an oscillator. So what that means is, when the CPU clock pulses once, that is basically one instruction. And it does this at an unbelievably fast rate. Okay. Huh, look at that. I have so much power. Rogue Ninja's gone in the bin. Anyway, I feel so powerful. Now for the registers, when the fetch, decode, execute cycle is going, you're going to have to talk about registers a lot more, but a register is a small block of memory. Normally it's based in RAM or normally the registers are accessed inside RAM and brought back and forward into the CPU. Now, if we haven't got data loaded in registers, then we've got no chance. Okay, the CPU needs to run information at a comparable speed. Now, this is why we can't just take things directly from secondary storage device. It needs to be brought to a device with a faster transfer rate, such as the RAM or cache. Cache has a faster transfer rate, and therefore we can load things onto the CPU a lot faster. Now, if you're asked to define, If you're asked to define what a register is, small block of memory. They are the keywords that I need to see, and they'll be in a mark scheme. A register is a small block of memory. It is temporary storage. Why is it temporary? Because it is volatile. Volatile means that if the power is lost, the data is also lost. Non-volatile devices, such as your secondary storage device, that means it retains the information even when power is gone or your computer switched off. All right? So this temporary storage runs at the same speed as the processor, or at least it tries to. And the processor contains many registers. So we've got some that are reserved for specific purposes, like the ACC, the accumulator, whose job is to do the addition. And others are general purpose registers. The PC, the MAR, and the MDR are all general purpose registers. I don't know who Snorlax is, but I'll tell you what you can have. You can have another timeout. There you go. I could do this all day. Oh, did it work? Did I time you out? Mm-hmm. There you go. Oh, double timeout. God, unlucky, mate. Right now. So, here we go. General purpose registers. We talked about those. They allow us to run calculations. Can be used for any purpose. Now, Some of the key special purpose registers. Now that should really say general purpose registers, okay? But popular exam questions are to explain what general purpose registers are. So that should really say, where's my pen? Let's do that. That's harder than it looks. So program counter, the MAR, the MDR, the current instruction register. I forgot about the CAR for a second. Okay, and that means your ACC is one of the special purpose registers. And that's just because it's located in a different part of the CPU. Now, the program counter, this is now moving onto the fetch, decode, execute cycle that Victoria was asking about. The program counter is the first register that's going to come into contact with data. The program counter is unbelievably important because it tells us where to start. So when we're trying to process instructions, it tells us exactly where to start from. And we increment the program counter every time we run a clock cycle. And that keeps track of how far we are into the processing of an instruction. So the program counter stores the address of the next instruction to be executed. Now, programs need to be loaded into memory by the operating system in order to function. If they are not in your primary storage, such as RAM, then you need to wait to go and get it from secondary storage. Okay? And that takes a lot of time in a computer's eyes. So in order to get access to this data, each piece of data comes with what we call memory addresses. And all we need to do is reference the memory address in order to get access to it. So think of RAM stored like loads of little mailboxes. If you've ever looked at Little Man Computer, you might have looked at that at GCSE or even A-level if your teacher's done it with you. Little Man Computer, it looks like a load of little post mailboxes. And that's where they're stored. And that's why one of the easiest ways to upgrade your computer is to put a new RAM stick in. There's a RAM stick there in the top corner. And you can put that in and that will increase the amount of information you can bring from your secondary storage device into your computer. So a very nice, easy, simple upgrade to your computer. So have a think now, use your brain and think, right, what will actually be stored in RAM? Are we just going to bring any information when our computer turns on? Or are we going to bring the most frequently used programs on our computer? And your operating system does all that thinking for you. It will bring all the most used programs and instructions into RAM for you. Correct. So when we've loaded our instructions, we need our program counter to point to the first instruction. So each instruction of the program is assigned a memory address. No, they colour it for the sake of it. And people put stupid RGB on it now, even on RAM. It's ridiculous. Anyway, the PC, the program counter, initially contains the address of the first instruction. So it includes the address, not the actual instruction. Remember, because the address links to the data. As the process is run, the instruction to which the PC is pointing is loaded into the memory address register. So what we do is we pass information, so the address that's the program count is pointing at, and we pass that over to the memory address register. So if you're writing this down, PC goes to MAR. Yeah, that's right. Yeah, you literally just plug a RAM chip in your slot, and that's it. Well done, though. So this process that I'm talking about now, taking or getting the address from the program counter over to the memory address register. This is the fetch part of the fetch, decode, execute cycle. Yeah, I'm going through the registers in order. Well, at least that's what I think I'm doing. Now this stuff is all just extra information that you're not going to need for your test, but it's good to know anyway. The value added to the PC is calculated from the size of the instructions, because sometimes instructions are broken down because they're too large to fit into the mailboxes of RAM. So we might have to split instructions up into subsections. So sometimes the value of the PC changes as a result of the instruction being executed. So sometimes you have to increment by 1 every time. Okay? Jumps are terrible, yes. If we jump between instructions, it's a lot more difficult for your processor to work out where you are. So jumping instructions is actually terrible. If anyone does electronics and you do assembly language programming, you want to try and limit the number of jumps to increase the speed of your program. That person never stops, exactly. They'll be back in another 300 seconds with another account, and I'm more than prepared to silence them for another 300 seconds. I could do this all night at the same time as doing a revision session. Memory address. Okay, MAR and MDR. Remember the order. PC goes to MAR. MAR goes to MDR. You have to get the address first, and then the address takes you to the data. So currently running programs are stored in memory, and then they must be loaded into registers. So this process is known as fetching. So that's the stuff I was just explaining before. And it makes use of 2 registers, the memory address register and the memory data register. You should be able to remember it because there's an A and there's a D. Now when we were teaching this at AS, while one instruction is being executed, another one is being fetched. And that is called pipelining, people. Pipelining. And that's just slightly increasing the speed of your fetch, decode, execute cycle instead of waiting around forever. Okay? Pipelining is what it's called. So in an exam, my advice to you, if I was a student and I was asked about the fetch, decode, execute cycle, I would remember this set of, or well, just this set. PC goes to the MAR. MAR passes the address so that the data can be taken from the registers, and it goes to the MDR. Okay? Then once we've got access to the data, we're then going to pass it to the current instruction register. Well, that's harsh. So, once we've got the data in the MDR, we're going to pass it to the current instruction register. Now, once we hit the current instruction register, that is going to be the decode phase. There you get off. That's going to be the decode phase of the fetch, decode, execute cycle. Okay? So have a quick read of that. And while you're doing that, I'm going to draw this out again. So you've got PC goes to the MAR. MAR goes to MDR. MDR goes to current instruction register. Now, people might have spotted that I've left out here the program counter incrementing by 1. Okay, as soon as this program counter passes over the address, then what we would do is we'd say PC plus 1. Okay, we'd increment the program counter so that it can start fetching while you are decoding and executing. Okay? So once it's in the current instruction register, this stage here is the decode phase. Oh, it's doing that thing again. Oh, we're doing right clicks again. This is not good. That should say decode. For some reason, it's trying to make me right click. This is the fetch phase. And then all we have to do is the last phase of this, last step, is the current instruction register. Once it's worked out what the instructions are, fires it out to the control unit. The control unit sends out the control signals. Oh, look at this. Oh, well done. Yeah, it is streaming in 1080p, or it should be. That's right, yeah. PC to MAR, MAR to MDR is the fetch. Yes, yes, yes. It shouldn't be 144p by default. Click on the settings. You don't have to divide it like that, Adil. You just need to be careful about the question, because a popular question that the exams ask is, how do you get data from your secondary storage device to the CPU? And this is how you do it. So you have to basically explain this piece of information here. You have to explain that. Obviously, you wouldn't just draw it like that because you wouldn't get very many marks. Okay? But there we are. So far so good. Now, one thing we need to talk about is the accumulator. Okay, any instruction that performs calculations makes use of the accumulator, even the part of incrementing the program counter. Believe it or not, yes, the PC getting incremented, that makes use of the accumulator because we're adding 1 to it. Now, calculations take a step-by-step approach, so the result of the last calculation is a part of the next calculation. And that's quite important because we need to take the result of all previous calculations and store them so that we're not losing any data. And your accumulator does all that for you. Now, next year, if you make it to computer science in the second year, you will be learning how to write assembly code instructions. So there's an example of work that's done inside your accumulator. We have the initial value of 0. We add 4. So we use the command add 4. And then we'll add 2. What's stored in your accumulator is the continuation. Then we subtract 1, and that's what happens. So the accumulator keeps a running total, basically. Don't do A2, it just gets worse. Yeah, that's true. It's true. But I'm sure these people are smart enough to make their own decisions. Okay. Now that is the sheet that I gave out to my students. Other students in other classes, you may have got that. It depends if your teacher give it to you, but that is the sheet that I made. Now if you look at step 3A, does that come straight after step 1? Or does it come after step 2? Well, apparently it makes very little difference if it's before it or it's after it. There's still a debate as to where it should go, but there is very, very little increase in efficiency. So it doesn't matter where you write it, as long as it's in your question that you increment the PC. That will get you a mark on its own by saying the program counter is incremented by 1. Okay. The exam is out of 100 marks. I think, or it's 90. I think yours is 90 marks. Yeah, it should. Yeah, all assembly language is the same. Yeah. So there won't be any change there. Okay, just go back, look at the start. So that's covered the von Neumann architecture and the fetch, decode, execute cycle. Okay. So moving on now, secondary storage devices. This is an area where students tend to do pretty good, to be honest. So I'm not going to spend too much time on this. But contemporary storage devices, if that's the way that the question expresses it in the exam, contemporary storage devices are just talking about storage. So that can be secondary storage, so that covers optical discs, so CDs or Blu-ray. It'll cover secondary storage like SSD and HDD. And it can also cover magnetic storage and cloud storage. So you might have heard of these devices before. These are called NAS, Network Attached Storage Devices. And all it is, it's just a series of hard drives brought together, really. Can be accessed anywhere in the world, providing it's got an internet connection. So it's just like a mini cloud, really, a mini data center in your home. So I've got a network attached storage device that holds all my information across all my computers so they can all access one place. And also, each disk inside there can be backed up using the RAID system, if you've heard of RAID before. Wow. Now, don't get virtual storage confused. So cloud storage is often referred to, well, cloud storage is the term that's been used most. That's our most popular term, but it can also be called virtual storage as well. And that covers things like Google Drive, iCloud. It'll cover a network attached storage device. It'll cover a personal storage device. So you might have seen, what's popular at the moment is you might have seen, this is a data center, but you have crypto miners now that have a similar setup, but just with GPU devices. But this is a data center that has lots of storage devices. So although you access the cloud or you access Google Drive, iCloud, whatever it will be, it still is a physical device somewhere else. So in class, we talked about where these are located. So think about where they're located. Usually they're in cold countries because they don't want to pay for cooling. Microsoft put their data center, put a data center under the sea because they didn't have to pay for cooling, and that was quite successful. But that's all about large scale storage. Virtual memory is something different. Virtual memory is when you use a secondary storage device as RAM. Virtual storage is storage in the cloud, basically. Right, so we don't need to cover RAID because that won't be on the exam. So let's just skip on past RAID systems. But you will need to understand disk defragmentation. Okay, defragmentation. So what is it? You might be asked to define what fragmentation is as opposed to defragmentation. So please do not get those two mixed up. Read the question thoroughly, otherwise you will lose marks. I've seen so many people lose marks because they've explained defragmentation when the question was asking for fragmentation. So when you add and delete different programs, or you remove data or add data, what it does is sometimes data can't be stored in one whole block on your secondary storage device. So what tends to happen is you delete things and it leaves gaps. The gaps aren't big enough to store data in, so we have to break up our programs, our instructions into different parts. So as that happens over time, your disk is known to be defragmented. Your disk is made to be fragmented. Now, fragmentation only happens on magnetic storage devices. So So that's your platters and your hard disk drives. Over time, you will need to defragment or bring back the information. So just like this image over here, you've got lots of different parts of your disk or blocks, contain different instructions, different programs. You want to get it in a more uniform pattern. If you look at the structure of a hard disk drive, then what you'll see is you'll see different sectors, clusters, tracks. No, there's no specific name for fragments, no. And you can see by the structure of a disk how easy it is for information to be spread out across lots of different sectors. Now, the reason why this is an issue is because the read-write arm of a magnetic disk has to move. I'm sure you're aware of that. So as the disk spins, its read-write head will try and cover different sectors and different platters, different clusters, different segments. And the more that read-write head has to move, the longer it's going to take to access your programs. So if we keep it all on the same track, the read-write head doesn't have to move as the disk spins, and therefore improves access time. So defragmentation is the process where files are physically arranged on a disk so that they're no longer fragmented. A popular question is to compare this process with what happens on secondary storage device. So a secondary storage device doesn't do any of that. If you look at the build-up of a secondary storage device, it has no moving parts. And if you're asked about that in the exam, I want you to say, the first thing I want you to say is a secondary storage device, such as SSD, solid state drive, it has no moving parts. It uses something called direct access. Okay? Direct access. Solid state. And because of that, everything's electronic. It can automatically reorganize itself using a trim command. Okay, a trim command is basically reorganizing, restructuring your disk. Okay, so be prepared to talk about fragmentation and defragmentation. Okay, compression's not on there, so let's go back now. So that covers secondary storage devices. Has anyone got any more questions on any of the secondary storage devices? The main two are hard disk drives and solid state drives. If not, I'll move on to network protocols. Very easy to get marks in this, but it's very rare you see a student actually getting top marks. Now here's just some information, just a background into protocols. If we don't have protocols, we won't be able to communicate online. Okay? In answer to the question over there, flash is solid state. So a flash drive or a USB drive is solid state, so that comes under SSD. And optical, no, you don't need to know about optical. Not for this assessment. Two main ones, like I said, are hard disk drives and solid state. Okay. Cache memory, that might come up under primary storage. So cache and RAM. And don't forget, you also have ROM as well. ROM is a primary storage. It's one of your primary storage devices. So protocols are necessary to specify data formats. So they enable devices to communicate with each other. And think about it, if we didn't have protocols, we would be lost as a global force, because every other country is making different computer systems, although you have your big giants like IBM, Dell, Microsoft, etc. All of the devices have to communicate with each other, whether it's on an Apple, Mac, or a Windows machine, for example. We have to be able to communicate online to send things back and forward. You can be using a phone, you can be using a tablet, and we use lots of different protocols to enable us to do that. So some examples of where protocols are used, things like linking a printer to a computer, a mobile phone by Bluetooth to your computer, and you've got using things like FTP, HTTP, SMTP, VoIP or POP3. If you don't know what they are, then that's what this next bit is about. FTP, File Transfer Protocol, HTTP, Hypertext Transfer Protocol, Simple Mail Transfer Protocol, Voice over Internet Protocol, and POP, Post Office Protocol 3. VoIP and POP3 you may not have heard of as much because we don't really cover them, but Voice over Internet Protocol is how you can ring somebody on WhatsApp, for example. So you can have a voice call over the internet. POP3 is a email client, an email protocol. Post office protocol, post office being letters, communication, that sort of stuff. So let's have a look at some. Okay, let's just go through them. Now these, in order to get the mark, these need to be pretty much word perfect. If you go off on a tangent and start talking about transferring files over a network, but you don't explicitly say large files over a network, you are going to struggle to get the second mark. These questions normally talk about defining the acronym. So never talk in acronyms if you can help it. So you never go around saying FTP, FTP, FTP. You always express that in the question. You always say file transfer protocols. Once you've mentioned it once in its full title, then you can start using it as an acronym. Okay? Now then, file transfer protocol, its job is to transfer large files over a network. That might be as an attachment on an email. It might be sending programs directly to someone over the internet. But it's important as FTP protocols have built-in error checking and retransmission requests. And think about that. It's important because if we send somebody a program online and it doesn't, all the packets don't arrive, then that program simply won't work. So the FTP protocol checks to see if the packets are good or not. Yes, Victoria, Maddie's right there, yeah. So data collision is where two pieces of data are detected on the transmission medium simultaneously. That's the actual mark scheme definition from my head anyway. I'll say that again. Data collision is where two pieces of data are detected on the same transmission medium simultaneously or at the same time. Hypertext transfer protocol. I've spoken to students in my class, and the students from my class, I've told you hypertext. Hypertext, where have you heard of that before? Hypertext markup language. And hypertext markup language is for creating websites. So if hypertext markup language is for creating websites, hypertext transfer protocol is transferring the multimedia web pages over the internet. And it's important because the HTTP protocol allows multiple different web browsers like Eclipse, Opera, Chrome, Firefox, you name it. They all display your web page in exactly the same way. Although sometimes they don't and they lie, but they should do. And it formats web pages as the original author intended. And that prevents web developers making 6 different websites for 6 different browsers. Happy days. Then we've got Simple Mail Transfer Protocol. So this one, SMTP and IMAP, often get confused. So this allows emails to be sent over a network. And it's important because SMTP provides a standard way of transferring emails between two different servers. That's important. That's the difference between IMAP and SMTP. Okay? Transferring emails between two different servers. And that's important if you've got an email that you're using on a domain rather than your personal email on your phone. Normally it's 2 marks, and they'll normally ask you for like 2 or 3 different protocols. And they will give you the protocol to start off with normally. They don't just say list 3 protocols and explain them. Normally they say, they normally say FTP, explain what that is, give an example. There might be a big question, I couldn't possibly say. Okay. Correct, yeah. This one, you see like there's 3 marks on this one. There's 3 marks on this because this is directly from an exam question. It asks you to define the acronym, it asks you to state what it's for and explain it, and then it asks you to state the importance of it. All right. So there we got IMAP allows emails to be transferred between computer systems via the internet. So IMAP is about computers and SMTP is about servers. And it's important as IMAP provides a standard way of transferring emails between 2 different servers. / messages are stored on the server instead of mobile devices. Now that might seem slightly confusing, but think about it like this. The way I remember it is I have my phone, and my phone I have the Outlook app, which is how I access my work email. And on my Outlook, it brings up the first 15 emails. And then when I scroll down to the bottom on my phone, it loads the next 15 from the server. And that means on my phone, I'm not using my phone's memory to store all the emails. I'm using the server's memory to store the emails and using the internet to bring them in. And that uses IMAP. That's why it mentions servers in that question. But it allows emails to be transferred between computer systems via the internet. Okay. Now, DHCP, Dynamic Host Control Protocol, this is to do with IP addresses, so Internet Protocol addresses. Every device you have on your network at home or in college has a IP address assigned to it. Now, there's not enough IP addresses in the world for all the devices that we have, so in order to counteract that, every time your device is switched off or you come off the internet network, then your IP address gets relinquished into a pool of IP addresses. And then what happens is when you rejoin it, you will be issued, using the protocol DHCP, you'll be reissued the protocol to your device. And it won't be the same IP address. IP addresses change all the time. All right. So it assigns IP addresses to devices on a network, and this is important as DHCP protocol ensures that the unique or dynamic IP addresses are allocated, and it allows addresses to be no longer in use to be automatically returned to the pool and then reallocated when we do need them. Yes, we're going to go through handshaking in a minute, Victoria. Somebody asked before about TCP, okay? Transmission Control Protocol / Internet Protocol. The only thing you need to know about that is that it's basically a suite of protocols, which means it's multiple protocols. So my browser might use multiple protocols together in order to take information from my computer, get it onto the internet, send it, receive it, and understand it. All right. Universal Datagram Protocol. Anytime I say UDP, I want you to think YouTube or some other video streaming service. So right now, as I live stream to you from where I am in my bunker, what I'm doing is I'm using Universal Datagram Protocols to send these packets of video information to you. Okay? Why has that gone? Disappeared. That should say, sends datagrams. Datagrams are just packets of video data, basically. But it sends datagrams across a network with very few error recovery services. Now, the reason why it uses very few error recovery services is because what's going to happen is I send information, it might drop out of 1080p and it might drop to 720p. And it does that because it's dropped a few packets in transmission. And then when my packets get sent properly, then it'll return back to 1080p. And it does that instead of just stopping your video feed. So we use that for audio and video streaming mainly. So we're not bothered about the odd lost packet here and there. We can continue with our life. Okay, and there we are for TCP/IP protocols. It allows network computers to communicate with each other. And that could even be in a LAN situation, a local area network. So you could connect your computer directly to another computer or even use your router at home and connect them and access all the files and folders from one computer to another via your router, for example. And that uses TCP/IP. You can also use it on a WAN, a wide area network. But it's important because the TCP/IP stack specifies how signals are routed and transported around the network using multiple protocols together. So handshaking, that is a 4-mark question, and it's the only one I've seen on handshaking. So describe the process of handshaking between two devices. Okay, firstly, I would have basically defined what handshaking is, which most students are quite good at. We've done that in assessments in the past. So handshaking is the process by which two devices establish their readiness to communicate. We have two main things in here, something called an SYN request. Okay, so you sync up the two protocols. SYN is used to indicate the start of a TCP session, transmission control protocol. Yeah, so it starts to put that TCP, basically puts the protocol together. And ACK is an acknowledgement that the TCP header is acknowledging the data. So you have an SYN request and an ACK request. All right. And it looks like this. So let's say we have a situation where we've got two computers, computer 1, computer 2. Device 1 will send an SYN request to device 2. Right? Basically says, hello, do you want to talk? And then this second computer then says, yeah, I do want to talk. Do you want to talk to me? So we send an SYN and that gets acknowledged, and then we send an SYN back. Both sides have to agree, basically. Both sides have to agree. So because you've got an SYN, it needs an ACK back, and that SYN that was sent from computer 2 needs an ACK back. We have to acknowledge it. Okay. Wonderful. Victoria, I've made you a moderator now, so you can delete their comments if you need to. Enjoy that. So you can monitor the live stream for me, thank you. Now, device 1 begins transmission. Okay? And that's what happens because we've agreed both sides. We've agreed on the protocols used from computer 1 over to computer 2, and we can get up and running. All right? Now, you might need to know what's inside a data packet as well. And again, students are pretty good at this. So data packets, they contain the sender's IP address because we need to know where it's going and where it's coming back to. So the intended receiver's IP address. And we need something that tells the network how many packets the data is broken into. So what we can do is we can basically say, well, this transmission has 10 packets. And if only 8 packets turn up, we know we're still waiting for 2, so we don't finish the transmission. We wait. And there might have been a collision, we might have dropped a few packets, we might have to retransmit. So also we need the number of that particular packet, and we need that so we can put them in order. So when all 8 packets arrive, are they going to arrive in packet 1, 2, 3, 4, 5, 6, 7, 8? Probably not if you're using packet switching. Okay? Now then, sometimes we have error checking. So error checking comes in the form of something called parity bits and checksums. We don't need to know what parity bits are and what checksums are. All we need to know is that the error checking is called parity bits and it's called checksums. Next year, you'll probably learn. I think, yeah, you do. You'll learn how they work in transmission. Now, yeah, someone's asked there. So basically, a parity bit is an extra bit used on the transmission to work out whether it's the data you've sent has been tampered with or it's been affected by the transmission. So it's a mathematical formula that basically works out whether those zeros and ones have been altered in any way. But that's just in a nutshell. Yeah. Again, it's probably because it's not needed, Zaki. You don't need to explain what a parity bit or a checksum is. You just need to know that's the kind of error checking we use on transmission. Okay. Now, what I'm going to do is while I'm on network protocols, I'm going to go through this transmission. I'll come back to logical operations in a minute, but this kind of closely follows networking itself. Okay? Now, these are really important. So if you are making notes, these are very, very important. So listen to my advice here, people. Next year, you are going to learn some new stuff and again, go over some of the old stuff in a little bit. Well, there you go. Thanks, Zaki. Perfect. So transmission, how you send packets or data from one place to another. We use something called serial transmission and parallel transmission. You can use either of these methods to transfer packets around. Serial connections always send one bit after another in order. So that's why you get long streams of zeros and ones, zeros and ones. And if you're asked for the advantages of serial connections, they are very good over long distances. Very good over long distances. Same with circuit, actually. So, parallel transmission can send more than one bit at a time. So for example, if you take out a cable like a VGA cable, if you know what that is, or a HDMI cable, they can send bits in parallel. So you can send a lot more bits down your cable at once. And back in the day, you used to have like a 32-pin printer cable. 32 pin printer cable. Madness. Absolute madness. Now we just use USB. A lot better. So instead of sending one long stream of bits, we send it in chunks of 8 bits at a time. So serial, parallel. Now moving on from there, you have the 3 different duplex modes. Because when a network is set up, the people involved in the network need to decide how the data will transmit between computers before we actually start sending it. Okay? And we do this while we decide on the protocols that we're going to use. So those 3 duplex modes are simplex, half duplex, and full duplex. Okay? Simplex, half duplex, and full duplex. Very popular questions to ask on exam papers. All right, so when we're setting up our protocols, we need to decide which duplex mode we are actually going to use. Do exam questions just ask you about duplex modes just to explain them? No, they don't. They will. The exam questions I've seen, normally they ask you to actually state examples of these 3 duplex modes. And there they are. So full duplex is where data can travel in both directions at the same time. Half duplex, data can travel in both directions, just like full duplex, but it's only one at a time. And simplex, data can travel in only one direction. Okay? So data in both directions at the same time, both directions but one at a time, and one direction only. So here's an example. Okay, if you're talking about one direction only, we're talking simplex here, you might want to talk about a satellite dish. Or even, sometimes in exams, what I've seen is they will give you a scenario and ask you to state which duplex mode you would actually use for that. Like they might say, what's a conference phone that can accept audio both ways at the same time. They might say, what about playing music on your computer where data is outputted to your speakers? Well, that's simplex, isn't it? Yeah, because data is only sent in one direction. We don't receive anything from our speakers, so that will be simplex. There is no return packets allowed here, and there is some information on that. That's just one good example to use if you're asked for an example. So satellites receive information. We don't ping information back with satellites, especially domestic ones anyway. You having a good time there, Victoria? See you've been busy. Now then, full duplex. You might recognize that cable. That cable is called a twisted pair, an Ethernet cable. So each pair is twisted together, and that allows for data to be sent in one direction and data to be received in the other direction. So full duplex makes use of separate wires inside the cable to send data back and forth. So a twisted pair cable such as a category 5, category 6, category 5E, category 7 now I think we're on, they would have twisted pairs for uploading and downloading. And that way, packets traveling opposite directions don't interfere with each other. And what does that prevent, people? That prevents collisions. When they're on different cables, it's going to prevent collisions because they're not going to be detected on the same wire if data is going in one direction or the other. And that's why we use Ethernet cables for transmitting internet signals or packets. And believe it or not, depending on the number of cable you're using, we also use Ethernet cable for half duplex. So it makes full use of all cables when transmitting data, but the flow can switch direction based on the communications needed. So if you want faster internet, you normally get a higher graded cable, and it can make use of half duplex as well. Oh, sorry. Yeah, half duplex. So packets can travel in either direction along the same line. Sometimes there are collisions. If those cables are damaged, or the sheath, the plastic around the copper is damaged, or there's even a strong magnet or a strong electrical signal next to the cable, it will weaken your signals, okay? And it can cause collisions. So they're not perfect, hidden away from collisions, these, but they do help prevent it, but they are still apparent. So for example, if you're at home and you receive absolutely garbage internet, see or have a look at your cable going for your telephone cable going from your house over the telephone line, see if it's near a power cable. Because if it is, it's actually weakening your internet. So check that out. All right, if we lose data or we have collisions, then the data must be sent again. We wait a short, random amount of time and send again. Okay. We're very interested to know. I wonder if these people are actually computer science students. Because if they are, my goodness, they're going to do very well. Anyway, so multiplexing. Multiplexing. Data transmission. When we send things, speeds can be increased by multiplexing. And the definition, the exam definition that you're going to need is multiplexing is a method where several independent data sources are combined and sent along a single route to a single destination. So think about it like you are putting all of the different cables or all the different inputs from different computers onto one cable to be sent out. Okay? They are combined and sent along a single route to a single destination. Okay. Now, several data streams can be combined and sent over the same wire, and think about the cost saving involved. We don't need as many wires, we don't need as many cables, therefore we're saving an awful lot of money. That's the main benefit. So, students tend to get confused between the stuff we were covering before, which was all the way back before our duplex modes. Where is it? Yeah, no, even further. So serial and parallel tends to get confused with packet and circuit switching. Okay? Serial and parallel transmission often gets confused with packet and circuit switching. So obviously, let's try and avoid that. So packet and circuit switching. So think about the internet. The internet is a large area network, all connected together. There's so many connections, it's going to be really hard to find the destination. There's obviously more than one way to reach the destination because every node or every router, every server, every cable is a part of that massive area network. So, There are so many connections that it'll be possible for a packet to find more than one way to reach its destination. Now, it's very similar to our road network in the UK. There are hundreds of different ways for me to get to work every morning. Some ways are quick, some are slow, some are just plain silly. They're going to take me forever to get there. So what I do is, the good thing about that is if there's an accident or there's roadworks, I can go a different route. And that means I'll still get to my destination, because the other situation is I'll just never get to work. I'll just be blocked. I couldn't get there. So networks have the exact same properties, and packets, the little clever packets, can have a choice of how they are routed. Packet and circuit switching are two methods of sending packets across the network with multiple paths. Victoria, I can't possibly comment on that. Now, packet switching, it's all about resilience. Resilience which means not stopping our data from getting it to its destination. So because of all the links, the internet is very resilient to broken lines or faults. If different parts of the actual network go down, it will find its way there. It might take a little bit longer, but you won't really notice it. There we go. One line is broken, another one can be used. One issue with having so many paths is that the route needs to be worked out in order to get from one PC to another. And believe it or not, when you send information from a computer, it goes to a data center, but it will go via your router, and your router will decide which is the best data center for it to go to, and then the data center will then look at its routing table and work out the right destination for your packet to go, and then it will arrive at the router of where you're trying to send it, or the server, and then it will actually get to the computer based on its IP address. All right. Briefly explain what the difference between serial and parallel. Yep. So serial is when you send data down a cable. Okay. Serial sends data down a cable 1 bit at a time. Parallel can send it in multiple bits at one time. It can send it in bytes, which is 8 bits. It can send it in a word length, 16 bits, 32 bits, 64 bits. And packet and circuit switching is how you send data in packets across a network. So not necessarily down a cable, but across an entire network. So if packet switching is breaking your data transmission, it's breaking your data down into packets, small bits. It'll send them across the network in different directions. All the packets don't have to travel in the same direction. They can go whatever direction they want. They can basically starburst and go off in all different directions if it wants to. As opposed to circuit switching, there's quite a big difference there. Circuit switching, a path across the network is set up in advance. Okay? So a path is set up across the network in advance. And all the packets are sent in order at one time. And what's the major benefit to sending all the packets in the same order down the cable? It's a question. Firing it out. It's not quicker. Not necessarily quicker. The key is sending it down the cable in order. Exactly, well done, Adil. The packets, when they arrive in circuit switching, they don't need to be reordered. There is a lag in processing time to reorder the packets. Because remember, what is contained inside a data packet? The packet number and the total number of packets. So like I said before, with the packets, if they arrive in order 1, 2, 3, 4, 5, 6, 7, 8, that's probably circuit switching. If it arrives 2, 3, 1, 5, 7, 8, 6, yeah, that's probably packet switching. Because it takes packets slightly longer, slightly shorter, going down different routes. So in answer to your question, Lewis, Victoria's put that there. That's a perfect exam mark scheme definition. Yeah, I would never ever say packets collide. Never. That's bad advice. Packets are detected near each other. They don't touch. Okay. Now, when you're circuit switching, because you are sending it in one direction down the cable, the route can't be used by anybody else, because it will interrupt and it will collide with all of your data going down the cable in one direction. Okay, it's good. It's nice to see you, Lewis, as well. All the packets on arrival will be in order, but the circuit is vulnerable, because if any part of the route is broken, the whole circuit will fail. So if I'm sending it to you and somebody decides to chop with some garden shears, chop my cable for my house, then I'm done for. That's it. Game over. I have to reattach the connection and go again. Packets can be intercepted by hackers, but yes, they are encrypted now. Well, if you're not sending them encrypted, you're an idiot. Yeah, question. Records will be in the exam, and how will it be worded? Yeah, I'll get to... I'll tell you what, I'll go to records next. Yeah. Go to record next. Now, when the route fails, the new circuit has to be set up before further communication can take place. So, let's say I'm on a phone. When I dial a number, the circuit is set up. So that number, the area code 0161 for Manchester, that sets me up to the data center for 0161. And then it goes to the exchange, finds the other phone on the other side, and we connect together. And that's why when you try and ring my house phone while I am on the phone, you get an engaged tone, because you're using circuit switching. Okay, if the line breaks, the conversation has to end and the number has to be redialed, and that wastes bandwidth. You don't want to waste bandwidth, especially if you're a gamer. So as one connection has been established, no other device can use the circuit until it's free, which is why I told my students about when I grew up, you either had the internet on or you could either make a phone call. You could not do both at the same time. And that's because the internet was using the telephone line. Okay, so I lived in an environment where if my mum wanted to make a phone call, I had to come off my games console. Why would you want to reducing latency? Get a better internet package. Okay, excellent. Now, just to reiterate, the packet switching is what we use on the internet, yeah, because they're very smart. Okay, packets are independent. They can go in any direction. Can't stress that enough. And you know what's contained inside a packet, don't you? Hopefully you do. So packet switching decides its own route. So when you get home from college and you try and go on your games console and you start playing online, you might find it is slightly more laggy, glitchy than normal. Okay, you will find that. And that's because a lot of people have obviously got home from work or college or whatever at the same time, and there's heavy usage on the entire network around Manchester. So right now at 1949, it's not that busy. So my load isn't a lot. Thank you, George. Clever stuff. All right. Packet switching is better because it's more resilient, but communication is not broken. However, packets don't arrive in order. So like I said, extra processing is required, and that slightly slows down your connection, but not a lot. Okay? And in summary, To put all that together, so this is for people that were confused before about serial connections and packet switching and whatever. So serial connections are always sent one bit after another. Parallel can send more than one bit at a time. Multiplexing, several independent data sources are combined and sent along a single route to a single destination. Then we move on to circuit switching and packet switching. Circuit switching, a path across the network is set up in advance and all packets are then sent in order down the same route. So the route cannot be used by anyone else while that connection is established. And packet switching allows packets to take independent routes through the network. Communication isn't broken, but it takes slightly longer to recombine the packets at the end. And also don't forget our duplex modes, people. Duplex modes. If they'll come up. There you go. So we've got full duplex. Data can travel in both directions at the same time. So conference phone or even like a Google Meet. That's a good example of full duplex because I can see you and hear you and I can talk at the same time. You can see me as well. So data's flowing in both directions. Half duplex. Both directions only at one, but only one at a time. So old-fashioned walkie-talkies where I have to talk and say over and then you have to transmit and then I can't transmit until you've finished. And then simplex speakers. Audio out only. Okay? Excellent. We're absolutely flying here, people. We're flying. We've done von Neumann. We've looked at the fetch, decode, execute cycle. We've looked at secondary storage devices. We've looked at network protocols. We've covered handshaking. We have finished serial and parallel transmissions or data transmissions. We have looked at duplex modes. We have covered multiplexing and we've looked at switching, which is packet and circuit. I'll come to Boolean algebra in just a second. Data packets we've covered. And I said I'll go through arrays and records and then we'll have a look at a few Boolean questions, shall we? So, arrays. Arrays. And you know what I'll do as well? I will send you this presentation as a gift from me. Actually, no, I won't send you the presentation. Oh, will I send you the presentation? I think I've got access to your Google Classrooms, students that are not from my class. I think I've got access to your classroom, so I'll post it on there. Lewis. Check the topic sheet. Does it say searching algorithms? I can't remember. I know it says sorting. Yeah, automatically goes up, Lewis. It'll be stuck on YouTube forever. Yeah. Okay, so if I ask you in the exam, explain or define what an array is. An array. Okay, a single dimensional array, also known as a list. Okay, a list in Python is not the same as an array. Forget about Python. I'll go through binary as well, Victoria. No problem. I've got you back. It's fine. Arrays. Single dimensions look like that. We have three things to remember with arrays. Three things. The first one is the identifier. How do we reference it? Okay. A collection of records that holds one data type. I would have said a collection of elements, but it's not bad. It's not bad. I would probably give you a benefit of the doubt mark for that high. So, identifier. Let's say this is called my array, right? So, my array. And I said 3. Okay? And if I wanted to output that in pseudocode, I'd write output in pseudocode. Output my array 3. That would point to the third index. These are the index numbers. That is how we reference and access them. That's how we access them. So if you are going to define what an array is, a single dimensional array, it is a data structure that holds multiple elements that are all the same data type. You cannot have strings and integers in here. In a list, you can in Python, but not normally. Okay, we're not talking about Python. Forget it. Okay? They can only hold one data type, be it an integer. a real value, which is a floating point value, or a string or a char, for example. Okay? You could have the weird situation where... Where's my pen gone again? Stop moving my pen. You can have the weird situation where these things in here are actually... They contain a record if you wanted to. We've done that in our programming, haven't we? Where elements contain a record of different data in there. All right? So you've got your identifier, which is the name of the array itself. We've got an element, which is the data inside there. And you've got an index, which allows me to reference it. And if I wanted to, I could assign this. I could get rid of output there. And I could say my array at the position of 3 is assigned 99. So this gets overwritten with 99. That's a single dimensional array. One row. Moving on from there, we have a 2-dimensional array. 2 dimensions. We're talking rows and columns here, people. So this here looked like our single dimensional array at first. These two. There you go. And then we added another row on. We added another row on. And it's the same. We have identifiers, we have indexes, and we have elements. The only difference is we have columns and rows now. So if I wanted to reference something from here, let's call, well, it's called X, this one, for some reason. So I could say X. You put the row in. Which row do we want to access? We want to access row... Well, these would have indexes normally. So it'd be like 0, 1, 2, 0, 1, 2, 3. Let's access 1. And let's do 3. So what value is there? Well, we're talking about this element here. The hardest thing to remember about 2-dimensional arrays is that it's row first. When you're accessing it, row first. Normally, it would, because it's an actual theory paper, it would normally be worded questions. That's what the questions would look like. It'd be worded. It would be explain, describe, that kind of thing. Explain the advantages, the benefits of using a 1-dimensional array. Or it might say, why would you use a 2-dimensional array? Are we having the programming exam next week or the week after? So next week, you have your exam on Monday. Then you are back in on Thursday. So all year groups are back in on Thursday and Friday. And then you have a week to prepare for the programming exam. And then you have your programming exam the week after that. That's the current plan. So 2-dimensional arrays is what you need to go up to at AS. And then, there you go. Grids and rows, they still only contain one type of data. And then we have records. Okay. Records have identifiers exactly the same as arrays. Yep, back in full time, Zaki. And fields, and this is the actual data itself. All right. Products. Now in Visual Basic, when we're programming or whatever, you would say dim my record as product. And that basically makes this variable of type product. And then, because you've done that, you've made a pointer to your record, you could then just say my record dot, put a full stop, and it will access all the fields. And you could say weight. And then you can assign it whatever value you want, 720 grams. Ah. Yep, you're having it in a week, yeah, Victoria. You can leave early, that's not a problem. It's free for you to come and go. I'll just keep going until I get bored. Or you get bored. Or you might already be bored. Who knows? There we are. But I'm only doing this for your benefit. Yeah, you can go. Yeah, don't worry, you can go. Sun's nearly set. You can nearly go and eat whatever you want to do. This will still be here anyway. I'll try and cover most things. Yeah. Yeah. Truncation. Truncation is not going to be covered, but there is a video on that somewhere. Now then, that's the information on records. So records are usually stored in files under one identifier. So it's a collection. A record officially is a... Yeah, I will timestamp it, no problem. A collection is a record, a collection, sorry, of related records under an identifier. No, it won't be on the exam. Truncation won't, and rounding won't be either. But the rest of the binary could be. So a record is a collection of related fields. Records are usually compared to arrays as they work in a similar way but can hold data of different data types. So records, different data types, arrays, one single data type. That is the main difference. Hopefully you can explain that. All right. Should we do some logic? Oh yes. Let's do some logic. Now then, this is probably one of the most difficult topics that people find. Probably one of the most difficult ones. Now, do you need to know the names of the laws? No, you do not. No, you do not. Do you need to know this bit in here? So this is for the OR rule. And this is for the AND rule. All right? So you're going to be able to know, well, you should be able to understand the symbols, firstly. These things down here, these are the general rules or the identities of Boolean algebra. You need to know them off by heart, how they work backwards and forwards. They will get you marks even if you cannot complete the full Boolean simplification. Trust me when I say that. Now, I believe people are pretty comfortable with logical operators and truth tables. And I say that every year, and yet there is still a small amount of the computer science population that just make really, really simple mistakes, and it's genuinely down to being too cocky. You think, oh, truth tables, yeah, no problem, I'll just do it, no problem. And you make one error, you have a 1 bit instead of a 0, and it's game over. So my advice, if you're ever going to listen to anything I ever say, ever, complete your Boolean algebra, complete your logical operation, truth tables. Then after the exam, when you've finished and put your pen down, okay, you've got a little bit of time left at the end of the exam, just go back and check it. Even if you are 100% confident, just go back and have a look. You won't believe the amount of papers that I've marked in my life. You won't believe the amount of mistakes I see people make. And it's like, it's very frustrating. But anyway, so you need to be happy with the tables. So you've got ANDing, ORing, NOTing, NAND, NOR, and XOR. Okay? So in this situation with AND, you only have a 1 when you have 2 1s involved. If you ever see a 0 in an AND, this is AND by the way, this full stop. If you ever see a 0, it will always result in a 0. Always. Always. Okay? So for this statement to be true, true is 1. Both inputs have to be true. So this is the only time when it's true. All right? To save a bit of time, if I was to P and Q and I was to not it, yeah, not these, then that would flip it, wouldn't it? That would flip every bit to the opposite bit. And that, when you flip it like that after you've ANDed it, that is a NAND truth table. I hope that's clear. So, because I do this a lot of the time when I'm truth tabling, I will AND first because I'm comfortable doing AND, and just to make sure I've not made a mistake, I will flip that table to produce this. I don't remember how to do a NAND table. I always do AND first and then flip it. It's just the way I am. Okay? or. Oring is when you see this plus symbol, and whenever you see a 1, you will always produce a 1. Always produce a 1 when you see a 1. 1, 1, 1. No problem. The only time you get 0 is when you have 2 zeros and you OR them together. And guess what, people? Guess what? If you knot it, it produces the flip of this. Who would have thought it? There's NOR for you. Amazing. People know these. I'm pretty sure they do. When you knot it, I talked about this, you flip it, no problem. Nanding, yep, we did that before. Noring, did that before. XOR is the only weird one that's a bit on its own, okay? We normally use, hey, whoa, hello, whoa, what's going on here? Right, the only time we use XOR, why is it trying to cut stuff? It's trying to cut, there you go. So the only time, why does it say cut? That's weird. The only time you get 1 is when you have opposites. So whenever you have a 0 or a 1, or a 0 and a 1, opposites produce 1s here, people. The same values produce nothing. Same values produce nothing. Do we have to do it step by step for NOR? No, you don't. No. How many people have we got, I wonder? We're dropping off yet? No. We're maintaining numbers. Yeah. NEXOR is just another term for it. But yeah. Anyway. So in Boolean algebra, you will see multiplication. What if there are 3 values for XOR? Do you mean? Well, they won't be, for a start. You will never have to truth table 3 values together like that. I know what you mean. You probably mean A, B, and C, and then XOR them together. You won't have to do that. You'll probably have to XOR A and B, and the result of that is then XORed with C, if that makes sense. That's the question they would give you. They wouldn't do that to you. Not at A level. Not even at A2. They wouldn't do that. So, in Boolean algebra, multiplication is replaced for ANDing. Don't worry about this weird stuff here. Conjunction, disjunction. They're just the formal terms. Yeah? Forget about those. Why is it trying to cut stuff again? Why is it doing that? Get off. You can ignore them. Absolutely no need to remember them at all. But multiplication takes the form of ANDing, and plus or addition replaces ORing. Okay. Now, quick go over the Boolean identities. Dominance, identity, idempotence, and complementary. Again, this is another perfect example of where I see students going wrong. I can only tell you what I see. I mark hundreds of papers every year. Hundreds of papers every year. And what do I see? 1 second. Let me just stop this for a sec. Let's discard that. Just reconnecting. Now, important thing to remember. Oh, okay. Is with my Boolean rules. Hopefully you can see that. If I have an A and I AND that with 0, you know that if I had the option when we use algebra, letters are just replacing values. That's what algebra is. It doesn't matter if you're doing standard algebra or Boolean algebra. Boolean, you know the word Boolean means true or false. I hope you do, because you're going to need to know about that sort of stuff. Okay? You know that. Let me just move this. My presentation's not working anymore. Great. Now, when I say algebra, oh, there you go, it's come back on. Amazing. You know that A could have the value of 0, or A could have the value of 1. You don't know. And that's the point of algebra. You're not supposed to know. So it could be either or. And all we're trying to do is make the best possible guess. We're trying to simplify it down as much as possible. So if I said to you, well, what if A was 0? If A was 0, it would be that, wouldn't it? 0 and 0, which is going to produce 0, because you remember your truth table. What if A was 1? Well, if A was 1, it doesn't matter. We've still got 0 in there, so it produced 0. So no matter what A is, it's going to always be 0. Always. What about A and 1? Well, if A was 0 and A was 1, you do the same thing again. You'd say 1 and 1 is going to produce 1, and 0 and 1 is going to produce 0. So if A was 1, it's going to produce 1. And if A was 0, then it's going to produce 0. So it's always going to produce whatever the result of A is. And that's why you get A. Now, apologies. I feel like I'm teaching you to suck eggs here, people. And if this is not new to you, where have you been? Now, A and A, you do the same thing. A can be 0 again, or A can be 1. Oh my God, this is incredibly stale. So you'd have 0 and 0, and you'd have 1 and 1, wouldn't you? And that gets you 0, and that gets you 1 when you AND it together. And what about not A? Well, if A was 0, and then you went and flipped its lid, it would be 1, wouldn't it? So if A is 0, then you're going to say A up. You're going to say, stop it, 0. If you flipped A, it'd be 1. Still going to produce 0, isn't it? And what about, all right then, what if A was 1 then? Well, it'd flip it, wouldn't it? So no matter what, because you're flipping one of the values, it's always going to be 0. So they're the AND rules that you really, 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 really need to remember, understand. If you have any questions or you don't understand why one of those is a 0 or why one of those is a 1, then please don't be afraid. Put it in the chat. I'll explain it again. No problem. The OR rules come in. And remember what OR means. So we did all the AND rules, no problem. Get off. A can be 1 or A can be 0. So you'd have this situation going on. And when you OR them, OR rule states that as long as you've got a 1, it will be a 1. That's why that always equals 1. A. Oh man, what are you doing back here? Get in the bin. There you go, gone. Gone forever. So in here, what about A? A can be 1 or A can be 0. You OR that with 0, you're going to get 1, you're going to get 0. So whatever A was is going to produce that at the end. So that's why it equals A. A can be 0 or A can be 0, 1 or 1. That's going to be whatever A was in the first place. That's why you've got A. And then finally, A can be 0 when you flip it. A can be 1 when you flip it. You're going to always get 1 in there. Now, you say it's confusing, you need to remember your truth table. You cannot work out these rules without remembering your AND truth table and your OR truth table. So that these numbers here, they are all the combinations that you can get with two inputs. So let's say A and let's say B. Okay, they are all the combinations you can get. When you AND them together, remember the AND rule from before? It states that if you have a 0 in there anywhere, it will always produce a 0 in the output. The only time you get a 1 is when the two 1s are together. If you get this and you're happy, can you just put it in the chat or something like that? So I know. I mean, I don't know how fast or slow to go here. This is very disorientating. 0, 0, 0, 1, 1, 0, 1, 1. Always good to have a nice little refresh of this stuff anyway. What does the AND rule state? AND rule states that if you have a 1 anywhere, it will produce a 1. So that gives you 1, 1, 1, and 0. It's the only place where there's no 1s. Yeah, got it, good, yeah, okay. Double negation. Double negation is a double not. You don't need that until next year, but basically you flip it twice. Simple as that. Now these help you simplify. So I'll quickly go through this, people, okay? Just I won't go through the truth tables, but I'll quickly just say that when you use the commutative law, it means you can swap things around. So A and B is the same as B and A. A or B is the same as B or A. Okay? Associative law means you can swap what's on the outside of the bracket to the inside of the bracket, providing the symbols are the same. So you've got and, you can swap it. Here, because they're all ORs, you can swap it. You can swap whatever terms you want in and out. Distribution is the same as GCSE distribution. You expand the brackets. Okay? You expand the brackets. Alright? Just like standard algebra. Okay, the reverse of that is factorization or factorizing. I hope your GCSE teachers were on point when you did this years and years ago. Absorption is probably one of the most common laws that we see. So, for example, A and A or B equals A. All of that simplifies down to A. Why? It doesn't matter why. All right? If you really want to get into it, find me. Yeah, find me when we've got a lot more time before the exam. All right? No problem. Thank you, whoever you are. And also, A or A and B equals A. Yeah, we prove absorption there. We prove De Morgan's. You don't even need to know De Morgan's yet anyway, okay? Now, in the future, you can actually practice these. In this presentation that I've given you, there are tons and tons and tons and tons of Boolean algebra questions, because I think the best way to learn this is to basically practice this, okay? Is to practice. So, I mean, if you got a question like this, think about this, right? On the paper on Monday, how much realistically can I get you to spend on these Boolean algebra questions? I mean, there might be 1 question, 2 questions in there. There might be a truth table. So there might be 6 marks for a Boolean algebra question on average, plus a truth table that might be 4 marks. There might be 10 marks on your paper. All right? Okay, so for this one, for example, the first thing I would do here is you distribute the brackets. So, I mean, I'll go through this one really quickly. This is A, B, A, so distribute that with that. And then I've got OR in the middle, followed by A, B, and B, like so. And then what you do is you look at these things here. So look at that there. Oh, what's this? Oh my goodness. This. What about this and this? Oh my days. Oh my. This actually leaves me with. What can I do with this? What are you on about? Anyway, B and A and B, because they simplify down. So that A and that A goes down to just A, B and B goes down to just B, and then, oh, look at that. It's weird, isn't it? Them two are the same things if you swap that around. Incredible. Incredible. Now, if you try and catch me before Monday, I'm more than happy to go through. I'll just sit here all day and just do like tons and tons of these things if you really want me to. But there's loads in here. Let's see what else we got. That one there, whatever that is. What is that? That's the... Don't know what that is. That is going to be X, I think. Don't know. You can work. Yeah, I think that's X. Yeah, that's X, I believe. Oh yeah, it was X. Look. Oh, missed it. Where's it gone? Yeah, it was X. There you go, question 4's in there. So there's loads of them in there if you really want to go through them. Happy to go through these with people outside of this live stream. Does anybody want to request a topic next? Now, I want someone to, well, people can request a topic in there. Yeah, sorting, I'll go through that. Data representation, I'll go through that. Yeah, no problem. One thing that I will say is make sure that you can clear, mask. You don't need to encrypt. It's an A2 skill. So clearing and masking also could appear on your paper. Can you let me know if you're happy with the clearing and masking, or do you really want me to go through it? People aren't really bothered. Yep. So, nice and quickly, right? If I said to you, here's a register, an 8-bit register, 0, what's that? 1, 2, 3, 4, 5, 6, 7, 8. If I said clear this register and state the logical operator used, the first thing you would do is write down and, yeah? That's the logical operator that you're going to use. If I write down here 0, 0, 0, 0, 0, 0, 0, yeah, that, if I and anything with 0, what's it going to produce? Zeros. There you go. Cleared. Job done. If you were going to XOR this, you would just produce the same input again. And you would XOR it, that's your logical operator, XOR, and this would produce all the zeros. So 2 ways to clear, okay? You get 1 mark for your logical operator, 1 mark for your what you call your mask, and 1 mark for the result. Happy days. Tick in the box. Masking, dead simple. 1, 2, 3, 4, 5, 6, 7, 8, right? So if I said mask this bit and this bit, make me a mask for that, then what you'd do is you would produce 1s in the requested bits. So this is what they call the mask. Okay? So wherever it asks you to show the bits, it'll tell you the least significant bit. This is the least significant bit if you didn't know that. This is the most significant bit if you didn't know that. This one's asking you to produce the 1, 2, 3, 4, third and fourth bit from the most significant bit. So it wants you to show the computer what those 2 are. So I've put them 2 as my mask, and then I use the AND logical operator, and I AND these 2 together. 0 and 0 gives you 0. 0 and 1 gives you 0. 1s give you 1 there. 0, 0, 0, and 0. Remember, the truth table in an AND gate says that if you AND these together, anything ANDed with 0 will produce 0. And this is the result. Happy days. Result. You get 1 mark for your result, 1 mark for your logical operator, and 1 mark for the correct mask. Happy days! Encryption. Don't need it. A2. You can do that next year if you make it. If you make it. Okay, clearing, masking, encryption, done. But if you do want to go through that a little bit slower, and I'm too quick for you, then there is notes on it there. Look, notes on it, 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 notes on it. Okay. Let's do sorting, and then I'll go on to binary. Sorting algorithms. Here you go. You need to know what the algorithms are. So the 2 sorting algorithms. Does everyone know what they are? 2 sorting algorithms that you've covered at AS. You need to be able to dry run those sorting algorithms using data. You need to know how to pseudocode them. And you need to know the best and worst case scenario for those sorting algorithms. People still haven't commented on what the sorts are. So the 2 sorts that we are looking for are bubble sort and insertion sort. We're not asking you. Thank you, Lewis. Oh, there's a lag, isn't there? I forget. Right, okay. So these are the sorting algorithms. The searching algorithms, if the topic list doesn't say it, it's not to be covered. So linear search and binary search are not covered. Okay, so let's have a look then. The bubble sort. Okay, the bubble sort has 2 iterations or 2 loops. The inner loop will always run n-1 times. Okay, n is the size of the array. Why? Oh, I've got no idea, John. 0, 1, 2, 3, 4, 5, 6. There's my array. They've got numbers in there. Numbers, 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 numbers. Okay? N is the number of times it's going to loop through the array. So this n would be 6. Because we're starting from 0, it would actually be 7, but it's 6 in this example. All right? Now, if it went through 7 times in total, because the number of times it's going to iterate, -1 would keep us inside the loop. In addition to that, if you just had one number, i.e. n, on its own and no other numbers in your list, would that array be sorted? Yes, it would. If you just had one number in the list, 14, and no other numbers, it's sorted, isn't it? Yeah. Okay. Then it has the job of moving the largest or smallest value in the list to the end of the list after the first pass. So if I was to run this algorithm and I was doing in ascending order, after the first pass of my array, I know if the bubble sort's correct, 19 would be up here. Because 14 would check with 15 and it'll go, you know, you're not bigger than it, so 15 stays there. 15 doesn't swap with 19. 19 swaps with 5. 19 swaps with 6. 6, 19 swaps with that. And 11. So that would be the first pass. And the passes are controlled by the outer loop of the algorithm. The inner loop controls the swaps. Okay? So the outer loop controls the passes. It will run if and only if no more values have been swapped. So the way to stop the way you stop a bubble sort is a pass is made and no swaps are done. And that's detected by a Boolean value in the algorithm. Swapped equals true or swapped equals false. And we're going to have a look at the algorithm in a minute. Would you just describe what it does for the algorithm if the question asks for that, Victoria? So if the question said, I don't know, for 4 marks, explain how a bubble sort works. You would explain what you see on the screen there. So that's the first point. That's how you describe a bubble sort. Let's have a look at the pseudocode for a bubble sort, because you might be expected to pseudocode this thing. Now, I'll annotate this for you so you can understand exactly what's going on. So let me just put this on screen. There you go. There we are. Now, when you run a bubble sort, normally you would run it as a procedure. So this is what my procedure is called, sort my array. All right. Now, you're not going to be penalized if you don't put this in a procedure, because you don't really need one. But it's good practice to do that. Now, we've got this thing. Remember when I said n is the number of items in your list? So this would be 1, 2, 3, 4, 5, 6. So 6 would go in there. So we have to declare the integer of n. N is the number of items. Temp. Now, we need a temporary value because we're going to overwrite it somewhere down the line. I'll show you why in a minute. I might do one pass of this. Swapped is Boolean. That's the thing that I was talking about before when I said there's a Boolean value. Swapped is true or swapped is false. And then we get down to line number 6. Set n. So set the variable called n to the length of my array. So I've already done that. I preempted myself there. We've set it to 6 because there's 6 elements in there. So that's that line done. Now we've got a repeat here. Repeat is also called iteration. So loop, isn't it? Repeat what? What do you want us to repeat, code? Repeat until, so this, line 7 is linked to line 17. Notice how all the code is indented inside it. That means that this loop controls all the code inside there. So it will only run this code from line 8 down to line 16 if swapped is false. Okay, sorry, what if swapped is true? Okay, so while a swap's been made in my algorithm, in my array up here, it will continue to sort it. Like I said before, a pass is made and no swaps are done. That is when the algorithm decides to end. Okay? Now then, it goes inside and it says swapped equals false. So here, swapped is false. And then we have this for loop. We've got a nested loop here. Nested means you've got a loop inside a loop. Oh, that's weird, John. Were you not talking about loops before? Yes, I was. The outer loop controls the passes, people. Passes. Inner loop controls the swaps. Swaps. Yeah, they're both loops. They're both iteration. One's a repeat loop and one's a for loop. So this is going to loop for I equals 0. Well, if I equals 0, I'll put that down there. To n minus 1. What the hell is n? Well, n is 6, isn't it? So this is going to be 6 minus 1. Oh, okay. Okay, so it's going to loop n minus 1 times. How strange. Were you not explaining that before, John? Yes, I was. If my array at the position of I, what's I? I is 0. So my array at the position of 0. So this thing here, number 6, that's the element inside there. So I could scrub all that out for 6 if I wanted to, because that just means if 6 is less than my array at I, which is 0, plus 1. 0 plus 1 is 1. So this is saying if 6 is less than 2. If 6 is less than 2, then do something. Is 6 less than 2? No. 6 is not less than 2. So we basically skip to the end if, hit the end for, and that means we go back up to the for loop because we've not finished this iteration yet. And when you hit end for and go back up and you start the next iteration, I goes from 0 to 1. So to save us all a little bit of time, the system then goes, okay, if my array at position of I, well, that's weird because we're not looking at this one anymore. We're looking now at this one and this one. So it says if 2 is less than 3. Well, 2 is less than 3, isn't it, people? Yes, it is. So this is the most important part of the bubble sort. This is the code that actually does the swaps. And look how it does it. The temporary variable is assigned my array at I plus 1. So that's this arrow here. So this data is put inside the temporary variable. I told you we're going to need a temp, and here it is, people. Then what we do is we say my array at the position of I plus 1. So this element here is going to be overwritten with whatever is in my array at I, at position of I, which is this one here, which is 2. So all of this gets overwritten with the value of 2. Now, if I didn't have this temporary variable, that number 3 would have been lost forever. And my algorithm wouldn't have worked. And down here, my array at I, which is where 2 is given the value of temp. So temp goes in there, 3. And then swapped, because we've actually made a swap, those values have swapped around, we set swapped to equal true. And because of that, then we go back up, we finish the end if, we go back up to the for loop, and we go again. So what your algorithm is going to do is it's going to say, is 2 less than 5? Yes, it is. So make a swap. So 2 gets swapped for 5. Then it goes, is 2 less than 1? No, it's not. Is 1 less than 4? Yes, it is. So 1 gets replaced with 4 and 1 goes in there. That is the first pass. And because this is true, we basically we start the pass again and we go through and we say, is 6 less than 3? No. Is 3 less than 5? Yes, it is. So we get 6, 5. Is 3 less than 2? No, it's not. Is 2 less than 4? Yes, it is. Is 2 less than 1? No, it's not. So this is the result after the second pass. And then what it does is it goes through finally and it says, is 6 less than 3? No. Is 5 less than 3? No. Is 3 less than 4? Yes. So them two swap over. So you get 6, 5, 4, 3, 2, 1. You get all the way, and that's the third pass. A final pass is made. It checks them all. No swaps are done. The array is sorted. Okay. If you want me to go through that slower, go to my YouTube channel, have a look at the bubble sort, and you can watch that video of me doing this algorithm in slow motion. In addition to that, you need to know the best and worst case scenario of a bubble sort. So what makes a bubble sort algorithm efficient? When the elements are already sorted and in order. Reason why that's the most efficient, because a pass is made and no swaps are done. Thank you, Charlie. So a pass is made and no swaps are done. Worst case is when all the elements are in the reverse order to what we want, because the first element has to bubble all the way up to the end, which is a right pain. Then the second element has to bubble all the way up to the end. Third element all the way to the end. Takes a long time. Whose mind is thoroughly fried? Moving on. We have the insertion sort. Slightly more technical, the insertion sort. But the insertion sort, it's still classed as simple to implement in regards to other sorting algorithms. And it builds on a final sorted array or a list, one item at a time. So it iterates or repeats its loop, taking in one input element at each loop, and then it grows a sorted list output as it goes. So at each iteration, the insertion sort removes one element from the data inputted and finds the location where it needs to be sorted or put into. So let me show you. Let me draw. Yeah, there you go, pen. So here we are. Here's my array again. 0, 1, 2, 3, 4, 5. Yeah, try doing a live stream for 2 hours and a half-ish. Let's do 11, 21, 38, 4, 5, 12. Okay, so what it does is you start with your array. Now we have to make space in this array. So what we do is we go, right, start at position 1. Okay, now this, imagine a divider in here. This stuff on the left of the divider is sorted. Is 11 sorted on its own? Yes, it is. What about all this stuff? This is not sorted on this side. So what it does is we interrogate 21, okay, and we put the line here. So we ignore this line now. And we've got 11 and 21. And 21 looks and compares 11. And it says, is 21 less than 11? If it's less than 11, then it needs to go onto the left of it, doesn't it? It needs to go here. Okay? But it's not. So it's in the right position because we're going in ascending order. So 11 and 21, they're in the right position. So what we do then is we increment up to 38. And we go, 38. Is 38 less than 21? No, it's not. And because it's sorted on the left-hand side of this barrier, we don't have to compare anything past this number, which makes it faster than a bubble sort. So we change our barrier, we put our line there to say all these things are sorted and all these things are still not sorted. Then we check 4. It's getting messy, this drawing already. We check 4. Is 4 less than 38? Yes, it is. So I'll put my barrier in. And I take 4 out, so 38 goes in there. Then, is 4 less than 21? Yes, it is. So we move 21. Is 4 less than 11? Yes, it is. So we move 11 in there. And then we put 4 in its rightful place because it's the end of the list. The specification says that you need to be able to pseudocode it, dry run it, talk about it, and list its best and worst case scenario. Obviously, the exam won't ask you all of those things, but the exam might ask you 1 or 2 of them. And you go through the list and you just keep moving that barrier up and comparing behind in the sorted part each time. Okay, so that's how the insertion sort actually works. Now, if you were to look at the pseudocode, that pseudocode explains exactly what I've just shown you in a drawing. So you've got all your integers. If I was to go through this, it would take me about an hour just to go through it. So what I'm going to do is I'm going to simplify it a little bit for you. Variables. Set n again. N is the number of elements. Then we have a for loop here, a do while loop here, and then a comparison here. All right? So what this does is this says for I equals 1. Now, why does it say I equals 1 and not I equals 0? Because, remember, the barrier goes in here and we start looking at this position. This is already sorted. 8 is already in its rightful place. So we have to start at position 1. That is key to the algorithm. Then we say n minus 1 because we've got 6 elements. Minus 1 means we're going to go from there to here. Then it says set the current item to wherever you are in your array. So current item would be 1 because that's where we currently are in the array. Set inserted equals false, false. And set j to equal whatever I is. Well, I was 1. Minus 1 is 0. Now, I keeps the position of what you're looking at, and j keeps the position behind the barrier. So j's pointing at that one. Stop doing that. There we are. So I is this one, and j is this one. And the reason why we use j is because j is responsible for going back down the sorted list to find the rightful position. So with this do here, this do says while j is less than or equal to 0. So do while j is greater than or equal to 0. So as long as j hasn't gone past 0, because there's nothing past 0, is there? As long as j hasn't gone down there and we've not made an insertion, keep going. So what will happen in the future is you'll get up here and your barrier will be there and 4 will be finding its place and it'll get inserted and that will break the loop. All right. The swapping part happens here. So this is when you actually swap a number. And what I'm going to recommend is I'm going to recommend that you go to my insertion sort video on YouTube and have a look at it. There's an animation in there that shows you how the insertion sort works, and I actually dry run the pseudocode as well. But that's the insertion sort in a nutshell. Just make sure that you can definitely describe these algorithms. Yeah. Like and subscribe. Now then. Best and worst case. Insertion sort has a fast best case running time if the input list is already mostly sorted. It's very efficient when it's mostly sorted because you don't have to keep going back in the sorted part of the list and reorganizing. The worst case for the insertion sort will occur when the input list is in the opposite order, same as the bubble sort, it's in the opposite order that you need. Okay, the opposite order that you need. Now, onto binary systems. The only thing we've not covered is 9, basically. So algorithms, so writing pseudocode, variables and constants, identifiers, scope of variables, local and global scope, parameters, passing by value, passing by reference, mathematical operators, greater than, less than, or equal to, that sort of stuff. And that's it for that. Now, binary number systems, I'll tell you what, I don't even need any of this stuff, really. Yeah, look. Yeah, don't even need it. Don't need it, don't need it, don't need it, don't need it, don't need it. Right. No, stop. Right, what I'm going to do is I'm just going to talk about... What I want you to do is I want you to put in the chat, if you're still here, if you're still alive and breathing, what I'd like you to do is you can tell me what you don't understand with binary. Because instead of me going through simple binary, converting denary to binary, binary to hexadecimal, addition, binary subtraction, looking at sign and magnitude, looking at 2's complement, looking at floating point binary. And if you don't need binary at all, you can also let me know. Understand it all, everything, all of it, like magic. Zaki, they don't have to do De Morgans, but yeah, great. Great. Right, okay, so quick recap then. We have something called sine and magnitude. Okay. Now this is all about negative binary. Okay. 2 methods of negative binary, sine and magnitude, and 2's complement. Okay. Sine. What is a sine bit? If you're asked in the exam what a sine bit is, what are you going to do? If you're asked what magnitude is, what on earth are you going to say? Oh my goodness. Oh my goodness. Now if I wanted to represent a number, let's do, I don't know, 21 in base 10. How can I represent that? How can I represent negative 21? Using sine and magnitude. So basically a sine bit represents the negative part of the number. And that will be a 0 or a 1. If it's 1, it's going to be negative. If it's 0, it's going to be positive. So when you look at an 8-bit number, for example, let's do it in 8 bits. 1, 2, 4, 8, 16, 32, 64, and 128. Now this, the sine bit, that 128 is no longer 128 when using sine and magnitude. It's 0 or a 1. Or a positive or a negative. Okay? So if I asked you to represent negative 21, then all you're going to do is you're going to go, well, 16. I've got 5 left over. So I can take a 4 and I can take a 1. So that equals 21. And everything else is 0. That represents currently positive 21. If I change that bit to a 1, it will now represent negative 21. Does... Oh, what am I doing? What are you doing, John? Have a word with yourself, mate. Here we go. Okay. Sine and magnitude. That's it. Now, if you were asked to explain what sine is, you'd obviously say the sine bit is a 0 or a 1. For a magnitude, this is the value of the number. Value of the number. What if you get a number higher than 128 to convert to negative? So if you got a number that's higher than 128, you would then look at the next number, 256, and you would use this 128 bit would be normal. You'd have to use 9 bits for that. But like Zaki says, you probably won't get that. I've never seen that on an AS paper anyway. But yeah, you'd use this bit, the 256, yeah? And that would be a negative, and this would be 128 positive. All right? Excellent. But please, oh my goodness, please make sure that if you see a number like this, if they just throw a number at you, they'll give you a box like this. Right? With whatever in it. They'll go 1, 0, 0, 1, 1, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, they'll throw a number at you like this and they'll say, convert that number using sign and magnitude. Okay? They'll ask you and they'll say, convert the number into sign and magnitude. Tell us the denary value of the magnitude. Please make sure that you isolate this bit and you only give the value of this. So this would be 1, 2, 4, 8, 16, 32, 64. This will be a plus or a minus. That's going to be a negative number. It's going to be 16 plus 8 plus 2. Oh, that's weird. 26. Okay, so it'll be negative 26. All right, be really careful. This is another situation. If you think about it, if you go back to your binary, go back to your Boolean algebra, and go back to your logic truth tables, and you double check those answers, people lose. These are your marks that you're going to get good marks on, these ones. You can't make mistakes on these. So please try not to. Now then, 8 bits. So using 8 bits, let's do the same one. Let's do negative 21. So 2's complement is slightly different. Normally, they ask you to explain the process. And there is 2 processes for making 2's complement, really. So let's do negative 21. So first, what you do is you do positive 21 again. So I'll do 1, 2, 4, 8, 16. I hope you can see this, by the way. It might be pretty small on your screen. I don't know. Flip it like a pancake. Thank you, Zaki. Slightly strange, but okay. So 16, none of them, one of those, none of them, one of those, 0, 0, 0. Okay? Thank you very much. So the process for 2's complement is copy up to and including the first one bit. So, okay, I'll do that now. Copy up to and including the first one bit. So, okay, there's the first one bit. So I copy everything, all the zeros up to the first one bit. Turns out there is no zeros up until the first one bit. So copy that one and then flip it like a pancake. I should really say flip the rest of the bits. So that goes to 1, to 0, to 1, to 0, to 1, 1, and 1. Okay, so now this is negative 21 in 2's complement. So the number, the positive number, was already in something called 1's complement. Now this one is in 2's complement. And if you can't do 2's complement, you can't do binary addition or binary subtraction. And why is that in 2's complement? Because this here now, when you do the flipping of it, this value is worth minus 128. So you go along and you take 1 minus 128, you add that to a positive 64, you add that to a positive 32, add that to a positive 8, add that to a positive 2, and add that to a positive 1. And that should give you negative 21 because you're working your way back from negative 128. Okay? The other method that you could also write is flip all the bits and add 1. From the least significant bit. Now, I don't teach that method because if I do teach you that second method, people tend to make more mistakes when they're doing binary addition and they're adding a 1 bit on the least significant bit. So if you've not my class, you wouldn't have been taught that because it would just confuse you. So literally just stick to copy up to and including the first 1 bit and then flip the rest of the bits. What next? What are we covering next? Victoria, did you say floating point binary? Floating point binary. How many people have we got? We're slacking. Must be petering out now. Wow. 15 viewers still. Some dedicated people on here. I hope you all do well in your exam. I'm sure you will if you've been here for the live stream. I'm sure you will be. Yeah, truncation. Truncation's not going to be covered though, Zaki, on this. Yeah, floating point binary. Okay. So, floating point binary. Binary subtraction. Apparently we're not doing it in these. Okay, yep. Right. So I might as well clear this then. Right. So floating point binary. I'll talk about binary addition if you really want me to. Do you want me to talk about binary addition? Right, let's just do binary addition really quick then for that one person. So we've got 1, 2, 4, 8, 16, 32, 64, 128. We'll do 8-bit binary addition. Now, let's take like super easy numbers because my brain's absolutely melting. Right, let's do that and let's do, I don't know, 18 something. Let's do 40 plus 18. Okay, 40 plus 18. So all I've got to do is represent these two numbers in binary. Okay, nice and simple. So 40, well-engineered numbers. There we go. You know that the answer is going to be 58, right? Surely you know that because you just add them up, don't you? Okay. Some people try and cheat on the exam. They'll just go, oh, that's 58. I'll just work out what 58 is and represent it. You don't get marks, funnily enough, for the correct answer. You get, for the correct denary number, you get marks for showing the method, the working out. That's the important thing here, people. The working out. So you do 40 there, so 32 and 8. That's 40. And then 18 is going to be 16 and 2. There we go. There we go. There we go. And there you go. Here we are. So now we've done that. You get a mark for working out the correct numbers. So you'll probably end up with 2 marks for that. That's not bad, is it? Okay. Now with binary addition, you need to remember that when we add 2 zeros like this, 0 plus 0 is equal to 1 0. Okay. When you have a 0 and a 1 like this, 0 and a 1, you have 1. Just 1, 1. Yeah, that's it. Then when you have a 1 and a 1, that gives you 0, and you use a carry 1. You carry the 1 over. Okay? When you have a 1 and a 1, and you have a carry 1 as well, that gives you 1, and you carry 1 over. I'll show you what I mean. Hopefully we have some carry 1s in this. Oh no, we don't. Okay, never mind. So we do 0 plus 0 gives us 0 according to this. 0 plus 1 gives us 1. 0 plus 0 gives us 0. 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. And the rest is 0 because that's 0 and 0. Okay, you work this out. You say, well, 32 plus our 16, so that's 48, plus R8 there, plus R2. So that's 10 plus 48 is 58, isn't it? So that was correct. That's the correct working out of it. Yeah, well, you can write it like that. You can write 1 plus... So, right, okay, that person's made a point there that this is actually 1, 0. That's fine. I was saying the reason I should have really written the 1 up there. So if you don't want to be confused, the reason why I put a 1 on the right side is because it's a carry bit. It's not actually a part of it. In essence, if I was to get rid of all this together, it should really be 1 plus 1 equals 0, and there's a carry 1 there. Should be a little 1. That's all it meant. Okay. Now let's say you had a situation, let's just make up and fabricate a situation where you had, I don't know, let's make a few of these 1 bits, shall we? So let's have a few 1 bits in there. Let's change the result. So this is to show you what happens when we have multiple 1s. And it's likely you would get carry 1s in the exam because the examiner wants to see what you're actually going to do. So 0 and 0 is going to be 0, and 1 and 1 is going to be 0, and you carry the 1 over. And that leaves you now, you see how I've produced 0, but we have a carry 1. This produces a situation where we've got 1 plus 1 and a 1. So it'll be a 1 written down, and you carry the 1 over. And then you've got the same situation of 3 1s, so you write 1 down, and you carry the 1 over. This now is 0, 1, and 1, which is 0, carry the 1, because you were running this situation here. Because we've got 2 1s. Then you've got 1 and 1 and a 0. So again, that's 0, carry the 1. 0, 0 and 1 just gives you 1 and 0. Okay. That leaves you with 64 plus 8 plus 4. I don't know what the numbers were, but it looks right to me. Okay. Now, you can probably work out now binary subtraction from this. So if I asked you, what is, I've got 40 and I want you to minus 18 from that. The process would be convert this number to positive 40, just like what we did before. Obviously that's not positive 40 anymore. And then you would represent positive 18 and then convert it into 2's complement. So what you would do now, if I just get rid of these, you take 40, positive. Then what you'd do is you'd represent 18, wouldn't you? Okay, you would represent 18, so with the 16 and the 2, rest are zeros. Now a little exam tip for you, keep it as neat as possible because the examiner is trying to work out the columns that you're using here, so try and keep them as neat as possible and it'll help you with your subtraction and your addition as well. Now when you've done 18 like this, what you need to do is you need to then represent negative 18 using the 2's complement method. You do not use sign and magnitude for binary subtraction. Okay, only 2's complement to represent negative 18. So remember the process? Go up to and including the first one bit. So you copy everything, all the zeros, up to the first one bit. And then you invert or flip the rest of the bits, like so. Okay, once you have established that, you now have all the ingredients you need to tackle the rest of the question, to actually add these two together. Because binary subtraction is actually binary addition of a negative number. So there we are. I wonder if I can move this up using my super skills. No. Okay, that's great, thank you. Rubbish, absolutely rubbish. Let's try again. Oh, the skill level. Yeah, kind of. So now what we do is we've got, oh, get off now. I spoke too soon. So now we've got that situation, we've got negative 18 and positive 40, and all we're going to do is add them together again. So 0 and 0, add them together. 0 added to 1 gives us 1. 0 added to 1 gives us 1. 1 and 1, that gives us 0, carry the 1. So 0, 0, 1 is just 1. 1 and 1 gives us 0, carry the 1 bit. Now, I will say again, 0, carry the 1, and 0, carry the 1. Now, point to note here, people, this is quite a good question because these carry bits, they get you a mark in your exam. So make sure you write them down. Don't just ignore them, write them down, you get a mark for them. This bit here has now made my, my value a 9-bit number. This is called overflow. So anything that goes past my 8th bit for adding two 8-bit numbers together gets ignored. Okay, it gets forgotten about. The number has overflowed out of my register, so I ignore it altogether. Yeah, you're welcome. Now, look at the number. This is 16 plus a 4 plus a 2. Okay? So that gives us 22. Yeah, and you can work out whether that's the correct answer or not. So that's binary subtraction. Okay, last question I'm going to do, unless people want specifics from me. Last question I'm going to do for tonight, because people are, their eyes are probably straining. But I do appreciate you taking the time to be here with me. Hopefully you gain something from this live stream, and I do hope you do really well in your exam. I'm rooting for you. I can't wait to mark the papers. Hopefully you've all done as well as you hope. So here we go. So floating point values. So the question, I mean, I've left a lot of the description out here, but the question might say, here is a binary number that's in floating point form, 40.75. We would like you to convert this number into binary. And it will provide in the question something called a mantissa and something called an exponent. Okay, or an exponent. You might have heard of them before from maths. Yeah, exponents are like them little to the power of numbers. Okay, that's what that's for. But all you need to remember really is, without getting too technical, this is the number of places you want to move the decimal point. The mantissa is actually the value of the number. Okay? So you'll get some numbers. They'll give you some numbers to use. So it might say using a, let's go 16-bit mantissa and a 6-bit exponent. Okay? So you need these numbers, and they are very important. And those people that I've taught, hopefully you remember the 4-step method that I taught you. If you've never heard of the 4-step method, you're missing out. If you follow it, you'll get these questions right 100% of the time. That is a John Batts guarantee here, people. So, step 1 of the 4-step method. Okay? We convert this number using the shortest number of bits. So 1, 2, 4, 8, 16, 32. Okay? So I can get a 32 in there, an 8 in there. There we go. There we are. That's 40. And what about 75? So that represents 40. I'm sure you'll agree. Then we put a decimal point after here. Everything to the left of 1 doubles, doesn't it? 1, 2, 4, 8, 16, 32, 64, 128, etc., etc., etc. Everything on the right-hand side of the decimal point doesn't double every time, it halves every time. So this is 0.5. And this is 0.25. And that would go on. And that means I can take 1 from there, 1 there, and I'll put my point in as well. Why not? That represents 40.75 in binary. Okay, you might think the question's finished there, but it's not. So that gets you 1 mark. Well done, you. So if you can do that, you'll get a mark. The next step, let's do it down here. The next step is to normalize. So you normalize the number. This number will be in 2's complement form. So what you have to do is you'll have to state whether it's a positive or a negative value. Currently, it's positive, isn't it? Yeah, it's positive 40.75. So normalizing the number basically just means put a 0 point at the front, because that's what a positive number has, 0 point. Then I'll just copy this. Now I'll explain a little bit more about normalization in just a second. There we go, there we go. And 1 and 1. Okay, now I've added a bit on. So I had 1, 2, 3, 4, 5, 6, 7, 8 bits before, and now I've got 9 bits. Normalization, all the computers in the world have to choose the same place to start with binary numbers in floating point form. So all manufacturers of computers decided that the 0 point, the point will come after the first bit. Okay? So that means all computers know where to start. Because if people were putting decimal points after the fourth bit, or the 3rd bit, or the 8th bit, or the 9th bit, the computers wouldn't be able to take in numbers from other computers if you got sent something or you were dealing with other data that got sent to you or whatever. We have to all decide where to start. So normalization, all you need to know is put 0 point at the front. I've never seen a negative floating point value question. So all you'll have to do if it's positive is put 0 point at the front. Okay, that's normalizing. And that increases your number by 1 bit. Then, the 3rd step of the 4-step method is to pad to the mantissa. Pad to the mantissa. So watch what I do here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. I need 16, 9, 10, 11, 12, 13, 14, 15, 16. I now have a 16-bit mantissa. This is my mantissa. It is 16 bits. So you have to pad using zeros to the right amount for the mantissa. You never, ever, ever pad on the left. If you put zeros at the front of your number, all these numbers get pushed back. And remember, when you shift things to the right, they half every time. So if you put the bits on the left, you would actually decrease your number by half every time. Your job is not to change the values. Your job is to pad on the right-hand side. This has no effect on your number whatsoever. So once you've done that step, you've padded out to the mantissa. The fourth step is now to work out the exponent. Okay, and we've got 6 bits to represent the exponent. So 1, 2, 4, 8, 16, 32. So that's 1, 2, 3, 4, 5, 6. So 6 bits to represent this. Now remember, it's in a 2's complement number, so this will be negative 32. And that will make no difference whatsoever to what you're about to do. So you see, might be quite difficult to see actually. But there's my first point in normalized position. This is my second point from the original question. And all I need to do is work out how many places this is going to move. It's going to move 1 place, 2 places, 3 places, 4, 5, 6 places. I need to represent 6 using 6 bits. No problem. There you go. I've represented 6 using 6 bits for the exponent. So now my answer is going to be 0.101.123. I'll put that point in, but you don't need to really. I'll just show you what it means. 110. Actually, I won't show you what it means. Then we've got 0, 1, 1, 1, 2, 3, 4, 5, 6, 7. Okay. Then you stick your exponent on the end. 0, 0, 0, 1, 1, 0. And that is your final answer. Okay, that will get you all of the marks for this question. So that's floating point numbers using the 4-step method. If you get asked to reverse this question, then that is quite straightforward. Also, reversing this question, all you have to do is read the information given to you and you reverse the 4-step process. So the exponent is 6, isn't it? So you go to the end of your number and you go 1, 2, 3, 4, 5, 6. So you chop off 6 bits at the end for the exponent. And it always goes at the end, the exponent. So this, you put your numbers on the top. So that's going to be 6. After you've done that, then once you've got your exponent or your exponent, you would then go from the point here and go 1, 2, 3, 4, 5, and 6. So you put your point in there. Once you've put your point in, you're good to go. You're good to put your numbers on top. 1, 2, 4, 6. Not what I know about. 1, 2, 4, 6. 1, 2, 4, 8, 16, and 32. Then these ones, because you put your point in, you know where your half goes and your quarter. And that represents 40.75. So that's the process reversed. Yeah, you do need to know data types. That is correct, yeah. But you must be pretty happy with data types. Integers, strings, reals, characters, I don't know if I said that already, booleans, But with data types, you might be asked things like, what would be a suitable data type for What would be a suitable data type for, I don't know, someone's name, someone's mobile number? What would be a suitable data type for someone's mobile number? That's an interesting one. String. Yeah. Yeah, it would be a string for a mobile number. Just remember, if you don't need to do any arithmetic or mathematical calculations, it doesn't have to be an integer or a real. Okay? The only time we use integers and reals is if we're using them for numerical values that we're going to, edit. Yep. Also, plus 4, 4. That's a good point. It's a character, isn't it? Yeah. How much marking do I have to do? Do I have to do specifically? I've got 15 T-level papers. I've got 2 classes of computer science, so that's about 44 papers. I've got A2, which is 43 papers. I've got about 23 coursework pieces to mark. Not a lot, not a lot. They could ask for the minimum storage requirements, yes, and that would probably be in bytes. Your test, it's out of 100, I think. Might be slightly less, might be 90 because of the reduced time because of COVID. We don't get our normal 2 hours. You think you get an hour and a half, so I reduced the paper. I will check. No, sleepless nights. No, you just remain very focused, and you get a lot of work done. Mock exams. Does anyone have any more questions before we finish? Because we're nearing 3 hours now, which is my normal live stream time. Just checking your paper. No, Zaki, no, I would never do that. Yeah, it's 90 marks, yeah. Oh, Victoria's still here. Fantastic. I'm sure he will. I'm sure he will. Okay, so there's still 18 viewers on, 266 playbacks, 24 likes. That's not bad. Yeah, 90 marks, not that bad. Mark a minute. Okay, so what I will do is I will send out this shortly, this presentation. And I'll get that onto Google Classroom. I do believe I've got access to all your Google Classrooms for the AS students, so I will post it up there for you. But like I said, thank you very much for coming. If you do have any more questions from now up until Monday, email me, jbr@osfc.ac.uk. I will timestamp it immediately after the live stream, so you can access the different parts that I've gone through on the specification. But yeah, thanks for coming, and good luck in your exam. I'm invigilating it, so I will be there, and I will see you on Monday. No problem. See you soon.